Hello everyone. Today I will be presenting the UMTEC project, a major technical achievement designed to support the extensions of France's nuclear power plant beyond 40 years of operation. The project, part of the VD4 900, addresses a critical safety objective, developing a modular water treatment system that can be deployed rapidly in the event of a serious reactor accident. This system, known by its French acronym UMTEC, Unité Mobile de Traitement des Eaux Contaminées, represents a significant step forward in strengthening resilience and safeguarding the environment. Indeed, in a world where the number of nuclear power plants is growing, it is more than ever really important not only to work on means to prevent and mitigate a severe accident, but also to be one step ahead and anticipate the post-crisis situation and ways to stabilize the long-term situation. I will briefly present you a bit of context, the genesis of the project, then I'll go further into details on the system itself. The outline of the operating principle, a focus on design of the consumable cartridges, which are the heart of the decontamination process designed by Veolia, a presentation of the control and monitoring principle of this system. And finally, I will conclude and present a quick summary of all the challenges which remain. So a bit of context. The Fukushima nuclear accident put the world spotlight on the management of the contaminated water following a nuclear severe accident. Minimizing the consequences required the very quick and reactive development of water treatment systems, in which Veolia took an important part in designing and commissioning, by the way. Back to France, in the instruction of the 4th decennial periodic safety review took place in the light of these events. It has brought a new approach to handling of nuclear severe accidents by taking into account not only the possibility of radionuclide dissemination through gas dispersion, but also from contaminated water leakage in the underground. Such an approach led EDF, our customer, to develop successive barriers to minimize the potential effect of such a catastrophe. The last of this barrier is to treat and remove radionuclides from the water inside the reactor building. And it's exactly what UMTEC is made for. To achieve this goal and to come up with a technical concept, EDF partnered with Veolia, world leader in waste and water treatment, as well as REEL, French industrial equipment engineering specialist. If we put the project story in this timeline, this is what we get. The first proof of concept in 2020, then the preliminary design phase, then the signature of a contract, as well as the launch of the detailed design and manufacturing phase. After 3 years of studies, testing and design, UMTEC is now approaching the final stages of its development. Today, manufacturing is nearly completed and the system is on track to begin acceptance testing, which will end up with delivery in summer 2026. And we should be on time for the French authority ASMR expectation. Here are the most important technical constraints that led the final UMTEC design that I'm going to present within the next few slides. First, it has to be a mobile system deployable on a nuclear reactor of the French fleet within less 3 months, 2 to 3 months. The performance, the contamination ratio has to be 100 in 2 months and 1 million within 4 months. The closed loop process, which means reinjection inside the reactor building, the ability to treat highly contaminated water, we are speaking about 1 terabecquerel per liter, the compatibility with current operating standards regarding radiological dose levels for operator. I'll go into details of that. So the system working principle is based on Veolia industrial water treatment technology and lessons learned from Fukushima accidents. The decontamination process relies on filtration and sorbent cartridges. How it works? First, in case of accidents, the contaminated waters comes from the reactor building. It goes through the pretreatment skid for temperature and pressure regulation. Then the regulated contaminated water goes through the removable cartridges mounted on the treatment skid, which is the main skid. First, the water goes through the filtration cartridges, then through the adsorption cartridges downstream. And finally, the treated water, the contaminated water, goes back to the reactor building. We have chemistry regulation and we have a lot of sensor. I'll go into detail later on. The chemistry skid will control the pH and boron concentration. The treatment process is expected to work up to 12 months, depending on the configuration. Up to 2,000 cubic meters of contaminated water will be treated. This means that each liter of water will pass through the system more than 50 times for decontamination. UMTEC comprises 5 skids fitted with standard containers, as well as replaceable cartridges. Everything is transportable by trucks. As you can see, we have 3 processes skid, the treatment skid, the main one, on which you can see the cartridges, the pre-treatment skid, on which the water comes from the reactor building, as well as the chemistry skid. We have 1 control station on the left, and we have an electrical distribution container. We have also a forklift, which will handle the cartridges. I'll get back to that later on. One of the most important lessons learned from Fukushima was the critical need to monitor cartridges loading. This requirement was integrated into UMTEC right from the start of the project. To address it, a dedicated tool has been developed to predict epuration, ion exchange by radio element. On the curve, the color curves show the radioactivity over time for different types of radio element. And the decontamination go down. The blue curves show the overall decontamination ratio over time. And it's 0 at the beginning and it's 1 million at the end. And by 2 months, it's roughly 100. This simulation is based on Veolia databases of physical, chemical, industrial processes built up over many years of experience. It provides a reliable way to anticipate cartridges' performance and to optimize the overall treatment process. I'll get back to the anticipation of cartridges replacement later on. Robust design approach. The final design is obviously the result of numerous technical compromises. First, the compatibility with extremely high radioactivity level, as I said, up to 1 terabecquerel per liter. Second, to meet all the transport and installation requirements. Third is a design reliable and simple for operation and maintenance. We are speaking about 40 years of maintenance and operation. And then manufacturing and supply chain limitation have been considered from the start of the project to come up with something simple and robust. Many calculations has been performed as far as dosimetry and safety performance. The outcome is a system compliance with standard operation requirements, so limited dosimetry and maximum of 100 operators over 12 months. So the design target are below 20 millisieverts per hour on contact and below 2 to 3 millisieverts at 1 meter. So that we are compliant with the standard in France for operators. The advanced features include the lead shield protection for safety, leak collection and re-injection system for containment, surveillance camera and real-time monitoring for oversight, firefighting system for emergency response, power supply redundancy for reliability, online water sampling with pH and dose measurement for continuous monitoring, among all the features we have implemented. Let's focus on cartridges design, which is really the heart of the system, the cornerstone of the system. So we have 3 types of cartridges design. The upstream filter cartridges in the process trap suspended particles present in the water. Then, so this is the cartridge on the left. Then we have sorbent cartridges, which contain material that capture radioactive element dissolved in the water. The design allows to fill the cartridges with the appropriate sorbent when required during the treatment phase. The simple adsorbent cartridge is similar to the one used in Fukushima. This is the one on the right. The annular cartridges, the one in the middle, has been specifically developed to handle with very high level of contamination. It allows a much better distribution of contaminated water to avoid any hotspots. I'll show you a short video which explains the differences between the cartridges. So this is the filter, the first one. This is the annular cartridge and the simple adsorption cartridge. Innovation in the design. So the final design of the cartridge is the result of numerous sizing calculation iterations in order to find the best technical compromise. Among many design parameters, most important are the maximum weight of 12 tons allowed for its handling, the pressure containment, pressure drop, and thermal constraints, cooling and ventilation constraints once loaded with very high level of contamination, filling and emptying functions, as well as interfacing with the treatment skid circuits. Last but not least, the requirement related to industrialization and mass production. Cartridges handling. Handling of the cartridges is a major aspect of the project, and deconnection to the main skin was one of the biggest technical challenges. We came up with the use of an industrial forklift equipped with a specialized lifting beam, as well as various assistance devices. The main objective is to facilitate and secure all operations of these cartridges. Control and monitoring. A team of 2 operators will be in charge of operating the system. 24/7. The control station team will be in constant communication with the operator in the forklift handling the cartridges operation, of course. And thanks to an intuitive INC system, management will be straightforward. The driving iSystem tool has been designed to manage cartridges replacement. Based on the Veolia database, this software has been developed specifically for this application. So this digital twin collects process data and calculates in advance the appropriate time to change the cartridges. The main objective of this tool is also to optimize the cartridges replacement frequency in order to achieve the contamination targets in terms of time. The combination of the two management tools will clearly ensure performance while maintaining a very high level of safety and reliability. Key challenges. To sum up, these are the main technical challenges we overcome to meet EDF requirements. First, the performance. The performance of the Veolia industrial decontamination process is the cornerstone of the system. And we have performed all the calculation, simulation, and test on prototypes level to demonstrate expected performance will be met. Second, the modularity of the system. Installation and commissioning on every EDF nuclear site in France. So within less than 3 months. And many studies have been done to enhance installation and commissioning sequences. Finally, the operability. So easy operation and monitoring within safety standards. User experience and user interface optimization has been developed to come up with friendly and easy to use system. Next step and conclusion. So we are proud of what has been accomplished so far. Designing and manufacturing of the UMTEC in a short amount of time with a partnership, a French partnership, French industrial partnership, and drawing from Fukushima experience. So for us, it's a first of a kind, and it shows the state-of-the-art supply chain experience in France. Very challenging and multidisciplinary have been put in place, and a lot of tasks in parallel have been carried out. Chemistry, radiochemistry, hydraulic process, safety, radio protection, operability, and manufacturing. As you can see on the picture on the right, this is the main skid, which is currently at the end of the manufacturing stage. And we want to thank our partners, CGLEC, REEL, AMCO, and Veolia, and obviously our client EDF for managing this project. The next challenges we have ahead. So for us and for EDF, this UMTEC system is definitely a game changer. It makes possible to increase the level of safety and to anticipate management of consequences of a serious accident. Indeed, with UMTEC, the system, which will be very soon available, EDF will be able to go a step further on the post-crisis situation, where the goal is not only to maintain confinement at all costs, but also to think of the future and to stabilize the long-term situation by considering the population going back home, and eventually the other reactor site could go back on the grid normally. This is it for my presentation. I guess we can start the Q&A session.
how does the system determine when a cartridge should be replaced? Is it based on predicted loading, online spectrometry, or a combination?
Yeah, to answer quickly, in fact, both. As Vincent mentioned, we have a monitoring. We have several several equipment measuring spectrogrammetry during the treatment. So we can monitor and we can control online what is going on with each cartridge, so that in fact we can say that we have online equipment measuring each time, and we have also developed a module to anticipate based on the loading of the cartridges, the radiological loading. We have a special module. We can anticipate and tell us when the cartridge will be completely filled. Of course, each prediction is updated when online measurements are made.
And the driving assistant tool, as you can see on the screen, inform the operator when it's time to change the cartridge and which one has to be changed.
Okay, thank you both, and thank you, Tandy, for asking that question. On to the next one. And this looks like a really good question. Will the treatment units only be built after an accident has happened, or will they be available in warehouse for just in case? The 3 to 4 month mobilization period seems long in case the units would be available from warehouse.
The system itself will be available in a warehouse. And this is the requirement from EDF and from the French Nuclear Authority. And for them, 3 months is enough. There's no rush, and the target is to decontaminate the entire volume of water within 8 to 10 months altogether. Jacques, maybe you can add something?
Yeah. When we talk about 3 months, we talk about 3 months after the severe accident. It doesn't mean that the power plant will explode at the beginning of the severe accident. Of course, generally speaking, it's not the case. Generally, the chronology of the accident show that you see what happened, and you can see what happened. You can anticipate a bit, just a bit. For instance, in Fukushima, there were several weeks between the tsunami, the loss of the control of the equipment, and the severe accident. This is a major hypothesis, but EDF made the hypothesis that between 2 to 3 months, they will be able to control, to manage the situation, to prepare, also to prepare the site so that people can go on and install the UMTEC. And we think it is realistic. We think we usually think from our feedback from Fukushima.
Thank you both. Let's keep the momentum going with this next question. Could you clarify the differences between the annular adsorption cartridge and the simple adsorption cartridge in terms of operational efficiency?
The annular cartridge is specifically designed for the beginning of the process when the water is very contaminated. The level of contamination is very high, and it has been designed so that we avoid hotspots and the thermal constraints anyway limit the volume of adsorbent that we can put within the cartridge. So that's why the annular cartridge is designed for. And once the contamination level decrease, so if I put this slide here, if we are on the right, so a few weeks or after, let's say 3 or 4 months, then the level it's much lower. So we don't have thermal constraints anymore. So we can use a bigger cartridge or a bigger volume of sorbent, and we use this standard adsorption cartridge, which has a much higher volume of sorbent, and we don't have hotspots issue anymore.
And just maybe to complete Vincent's answer, as you can see on the annular cartridge, there is a lot of pipe inside, and we also the development was made for treatment, water treatment, but also for storage after filling the cartridge. So after filling the cartridge, it is drained of its water and then store and we have to manage hydrogen due to water radiolyze. So all those pipes you can see inside are designed specifically to generate self-aerated self-aeration inside the cartridge and avoid high concentration of hydrogen.
The tennis question is this: could UMTEC be adapted for other radiological or industrial contamination scenarios beyond nuclear severe accidents?
Yes, obviously yes. Actually, the system is based on Veolia industrial decontamination knowledge and experience within industrial, let's say, field. The sorbent and the filters have been just customized, let's say, and radio protection has been put in place, and all the features linked to the radiological constraints. But as far as contamination itself, it's very, let's say, similar to other types of industrial contamination. Maybe Jacques, you can add something on that.
We have also a lot of knowledge on how to choose sorbent, and we have an internal database that we can use to predict which sorbent for which element. So it's quite easy. I can say it's possible to adapt this for other radiological elements due to our knowledge. For instance, for UMTEC, we have performed tests at the beginning of the study, and at lab scale on inactive element and also on active element, and in our screening, it's about 30 sorbents which have been tested and for test and classify, so that a sorbent is we can choose a sorbent as a combination of what is your technical need. I mean, what element you need to remove, but also there is also we can also add some economical criteria, and also we can also adapt the overall treatment. For instance, as you can see on that slide. Yeah, as you can see on that slide, if you see these element here, strontium, you can see that at the beginning of the treatment, it's not a major one. The major one is cesium. But as strontium is not well removed by the sorbent selected at the beginning of the treatment, at about 2 months, it becomes a major one. So we have to adapt. We have to adapt our treatment depending on which is inside water at the beginning of the treatment, but at each step of the treatment. It's and that is the main that is one of the main feedback this is one of the main knowledge we use for managing this system.
Great, thank you so much for that in-depth explanation. We've got quite a few more questions here. So let me ask this as the next one. And this was in regards to the cartridges. So they asked about, what about the exhausted cartridges?
At that time, we have no. At that time, we have no way for. And we have no disposal for this kind of cartridge. For instance, annular cartridge will be very contaminated. For instance, with a thermal power loading at around 1.4 kilowatt. That means there is a lot of things inside, lot of people inside, and we managed. This was not the key point of the treatment. It was not to think about the storage of the filled cartridge, but we take it into account. We have designed a building, a special building for first temporary storage and then long-term storage.
Actually, the cartridges, once loading, will become a final waste, and the final disposal of this waste is not decided yet. This will be decided later on. But what has been designed is something that is safe. Each cartridge, when it's loaded, is fully empty of water, and there is a filter, a very high performance filter, which is used to maintain contamination within the cartridge itself. So this is a final safe waste, and it will be disposed and somewhere close to the power plant, probably. But it will remain safe for a very long time.
Fantastic, thank you both, and I hope you answered that question, attendee. Now let's dive on to the next one. So this is in regards to the radiological protection. They asked, in order to minimize the dose of the operators, they were wondering if the unit can be remotely operated, and have you thought of using a drone to supervise that everything is okay around the unit?
Remote operating has not been required yet, but it may be required in the future. So it's not going to be an issue. We know that, for instance, the forklift or the operation of the cartridges will be possible to be remotely controlled, so that's not an issue. The design has been, or we put lead shield all around because we believe some operators will have to go or will have to do some maintenance tasks. So that's why at the beginning we designed the system to be able to handle operators around. Jacques, maybe you want to add something?
Yes, I can also add that in case of biggest maintenance, UMTEC can be completely drained and washed, so that we could this level of contamination you see, this dose rate, is a dose rate in operation at the beginning of the severe accident with the maximum activity of water. It will not be this is the worst case, but we are able to decrease this level by washing the machine, so that in case of special maintenance, we think that this level could be highly decreased.
Great, thank you. And then just another reminder to our attendees, you can still ask our speakers questions. Now on to the next one. This looks interesting, and it's in regards to the filters. How many filters will you have in storage or stockage, and what is the expected production time for new filter packages? Are the necessary components available?
Yes, the filters have been manufactured in the same time as the skid themselves, and it's around 200 cartridges which have been manufactured and will be or are currently being manufactured, and together with all the skid will be ready to be installed, and the sorbent will be filling just before usage. So it's the cartridge themselves will be prepared just before they will be used on the UMTEC system. So maybe Jacques, you want to add something on that?
Yes, yes, I have something. And as you mentioned, cartridges are manufactured. They are stored by rail, and at the beginning of the treatment, the first thing to do is to analyze the composition of water. So we use also UMTEC and its spectrogrammeters online spectrogrammeters to measure what is in the water, because all the scenarios we have mentioned are based on an hypothetical composition of water, but it could at the moment, if we need UMTEC one day, it could be a different composition. The first time is to measure this composition, and UMTEC is made for that. We have spectrogrammeters online. We also are able to make some samples, and then to go to the lab, for instance, to measure alpha or beta emitters, which can be more problematic. And the idea is to have high knowledge of the water. I mean, as high as possible, with and it is included in the design of UMTEC.
Okay, thank you both. Okay, so we have a few more questions to go through. Thank you very much to our attendees for all these fantastic questions. Now here's another one. These technologies can be implemented on existing ones, or is it necessarily for new buildings? So what are your thoughts on that?
This is for existing one, and this is, I mean, as long as the interface in and out water is available on the reactor building, we can adapt, and the UMTEC is adaptable to any kind of reactor. Actually, it's the water which has to be decontaminated. So there's no link with the technology of the reactor itself. We are dealing with the contaminated water. So whatever the contaminated water, UMTEC is able to, as long as we have an interface, to treat the water. And as Jacques just said, we have the ability to do sampling of the water so that we can customize the sorbent and all the parameters of the treatment. Jacques, maybe you want to add something?
Oh, no, nothing more to add. For EDF, this connection is EDF modify all of his nuclear plant to have a connection for UMTEC. So it will not be a problem for the French nuclear plant facilities.
Thank you very much. Now we have a couple more questions. I'll ask these two before we conclude our Q&A. And the question's directed to you, Vincent. So did you link your answer in regards to the high radiation levels at the start of treatment with thermal loading on the IX column, or is the IX process exothermic?
I mean, the radiation and the protection of the lead shield protection, for instance, what we can see on this picture, has been calculated so that the operator are safe, or so that the level are, let's say, acceptable. And within the cartridges, also, maybe we missed to mention, but on all the cartridges, there are something like 15 centimeters of lead around. This is what we can see on this cut view. And this is the purpose of this lead shield is to be able to be close by the cartridges once we handle them, once loaded. For instance, on the forklift, we have an operator who is protected with lead shield glass, and also with the lead shield of the cartridges themselves. So the forklift operator is safe, or is in the, let's say, acceptable level to handle and to carry on operations.
Concerning the exothermic process of adsorption, we didn't notice any exothermic behavior during our labs, our test at the lab.
The temperature will decrease over time.
And with that question, I'd like to conclude our Q&A session and webinar. I want to say thank you to Vincent and Jack for their fantastic insights, and also our attendees for all these great questions. Thank you for joining us today, and I wish you all a wonderful day ahead.
Thank you.
Thank you.